We have just seen that we have three formulas that tell us the potential energy that is stored in a capacitor when it's given a certain amount of charge Q or charged up to a given voltage V. It'd be nice, though, to verify that this energy that's stored in there, our formula for it, actually corresponds to the actual energy it takes to charge up the capacitor. If it does do that, then we know that whatever energy we put into charging the capacitor actually will reside there as potential energy that then we could potentially get out. And then we are truly functioning as an energy storage device. So let's then try to compute. Our goal is going to be now to compute the charging energy of a capacitor and then compare it to our formulas that we have here for the potential energy stored in a capacitor. So let's take a look at this particular question then of charging energy for the capacitor. So to help with this, let's just consider a very simple diagram. It's getting hard for me to keep drawing these three-dimensional diagrams. So let me just give you an edge view of my capacitor as I think about this charging energy. So my edge view will look something like this. You will just see the top plate here and the bottom plate down here. And I'm going to imagine that I'm charging the system here by moving charges from this bottom plate up towards the top plate. I'm going to move those charges one little charge at a time, dq. And I'm going to start with neutral plates, and I'm going to be moving this charge from the bottom plate to the top plate. As I do that, the top plate will then start to carry a positive charge. Somewhere in the midst of this process, the total charge up here I will call plus Q sub n at the nth step after I've moved n little charges from the bottom to the top. As I move those positive charges off the bottom plate, of course, ends up negative. So there will be a charge minus the corresponding amount of charge on the bottom plate. And my goal then is to vary this Q sub n from 0 all the way up to capital Q when I have a fully charged capacitor. So that then is how I'm going to compute the energy that we're putting into this charging energy. I want to determine the work done by us as we carry out this process. And that work done by us, we can follow our standard rules, right? That's going to be the work that we do at each of these steps to move our charge dq. Now, the work to move a charge dq, that we already know, right? That is by, our definition really of work and its relationship to voltage. The work to move these little charges dq is proportional to the amount of charge dq, and the proportionality constant then is the voltage from the starting point of where I'm beginning my charges, that's on the minus plate, to the ending point where I finally deposit the charges. So that is this voltage. Now, our next step is to realize, and of course, I have to sum over n, right? Each step in this process until I've finally fully charged my capacitor. I want to add up all of those energies. Now, we know something about this voltage. We're given a certain capacitor, so it's reasonable to say that we've somehow worked out somewhere else the actual value of the capacitance. So I'll write C here to represent that value. That's useful because then the voltage from the minus to the top plate we know from our terminal characteristic. Remember that for the capacitor, the amount of charge Q at any time is equal to the capacitance times whatever the voltage is. Q equals CV. Because of that fact, I can re-express this voltage then simply as the amount of charge at the nth step because this voltage clearly will be changing as I've moved more and more charge, but at the instant I'm moving this dq, the amount of charge on there is q from that nth step, and I can then divide by the capacitance. Now, what I hope you are starting to see is that I've set this up here as some kind of a Riemann sum. At the end of the day, I want to take this limiting process where the dq's become very small, and in the limit then, as I do this process with many, many very tiny dq's, what I'm finding is that the total work that we are putting into this system has to be equal to an integral of q is my integration variable when I convert to an integral, q divided by c times dq. And this integral, I have to list the range of my integration variable q. Well, q has been varied from 0, my starting point, to capital Q at the end of the day. So now all that's left for me to do is to carry out this integral and hope that the work that we put in to charge this actually shows up as potential energy, actually corresponds to one of these three forms for the total potential energy. 1/2 CV squared, 1/2 Q squared on C, or equivalently 1/2 QV. So let's see. Let's carry out the integral. This is kind of getting exciting. I hope the energy ends up being conserved. I'll not feel very good if it doesn't. Well, we know how to do this kind of an integral. C is a constant. I can certainly factor that out. So I'll have 1 over C. Then I will have the integral of Q dq. Well, that's what, like the first integral that you learn. That's Q squared over 2 is the integral, right? Because the derivative of this would carry down the 2, and I just get my Q back again. And that has to be evaluated between my limits of integration, capital Q and 0. Substituting in, that gives me 1 over the capacitance times big Q squared over 2. Oh, this is looking sweet. 0 squared over 2. Of course, the 0 is just going to give me 0. So the work done by us, in this particular case, the charging work, turns out to be Q squared, look at that, Q squared divided by 2C. That's the energy that we put in to charge the thing in a circuit, and that matches exactly the potential energy stored there, so we can get that energy back out later. We really do have an energy storage device. That, again, whenever energy is conserved, that leads to a happy professor. So I'll give us here our happy professor symbol. And I thank you for listening, and we'll continue these investigations.